because if you accept, well, that's one way of halting. Okay, so if it doesn't halt, therefore it doesn't reject and it doesn't accept. Right? So if R says, if R comes back with reject, that means that M does not halt on W. Okay? Now you're simulating this, right? Your S. So R is now giving you some vital information. It's told you whether the order pair MW is going to halt or not. Right? Now if R tells you that it doesn't halt, well, therefore you know that this MW as a member of this language, if it is or not, cannot be a member of that language, because if this is a member of that language, then M would accept W. But R is saying that R is saying that W does not cause M to halt. So therefore you reject that it's accepting, that M cannot be accepting W. Right. Okay, so we know that that ordered pair is not a member of that language. Okay, so that means by putting this ordered pair through R, you know whether it's halting or not. Okay. Now, if it's not halting, just reject. As S, because you're simulating this. You're trying to decide this. Okay, so you use R to see to check whether it halts or not. If it doesn't, if R says it doesn't halt, this, then as S you reject, and so you have that information. So now you know whether it halts or not. So if it does halt, if R tells you that it does halt, well, then you just keep simulating as S. You just keep simulating until you get until it does halt, because you know it's halt. R's told you it's going to halt. So you just simulate until either it accepts or rejects, and if it accepts, well, as S you return accept, and if the simulation says that rejects, well, you return reject. So in other words, for any ordered pair, so any element, you've decided, right? You either accept that pair or you reject that pair. So you have shown that S is a decider of this language. Okay? I hope you follow that logic. Okay, so in other words, if R exists, then by what I'm just saying here, it means that we can decide ATM by using S, and S calls on R. Right? So if R exists, then we can decide ATM. But we know from prior knowledge that ATM is undecidable. Right? Well, by proof by contradiction, therefore R cannot exist. Okay? And if R doesn't exist, well, therefore halt TM is undecidable. Now that's actually, that's the proof idea. And here's my question again. Where is reducibility coming into this? Seems to me it's just a straightforward example of proof by contradiction. So where is reducibility coming in? It's not clear. I mean, he states, the key idea is to show that ATM is reducible to halt. Maybe. Anyway, here's my question to you. Take it as homework if you like. Think about that. I'll play devil's advocate. In this case, I don't need reducibility, true or false. Right? Seems to me just a fairly straightforward example of proof by contradiction. Alright, okay, so that's the idea. Now the actual proof. again, of course, by contradiction. So so we assume that this language halt is decidable. Therefore, by definition, there's some Turing machine that decides it. We'll call it R. Okay, and then we'll construct a larger Turing machine S that uses R as a component, and this S will decide this language. Okay, and okay, so if there is an R, then by using R inside S, we can use S to decide ATM, and that's the contradiction. Right? So that sort of logic is the same, well, of course, as in the proof idea. Alright, now a bit more detail on how S actually operates. So S operates as follows. Now here's your formal, well, your standard format description of an algorithm. In other words, how a Turing machine operates. S. Remember, an algorithm is just what a Turing machine does. Okay, so as usual, you start with a description of the input tape. So if this ordered pair, the encoding of it, encoded information about two things, some random Turing machine M and some tape that goes into it. Okay, so these two things, so the information of these two things goes in. And then the various stages in the algorithm, numbered. So, firstly, you'll input this ordered pair, this string, into R. Now remember, R decides. It will take this and it will accept or reject this. Right? It won't loop because R is a decider. Right? R decides halt, and this is a an input string. It's a member. It's a member of halt. Right? This. Wait a minute. No. Forget what I just said. It's just a random machine and a random string. Okay. And it just goes in. And R will accept or reject this pair. It'll accept if this pair belongs to this language, and it will reject this pair if this pair does not belong to that language. Okay, yeah, that's correct. All right. Now, if R rejects, in other words, this pair does not belong to that language, well then as S you reject. Right? Now, if R accepts, in other words, this pair does belong to the language, then you, as S, you just continue your simulation. But now you've got this knowledge, thanks to R, you know that your simulation is going to halt. Right? By using R, you have eliminated the possibility of looping in your simulation. So you now know that looping is not an option. Right? You know that your simulation will halt one way or the other. It'll either accept or reject. Okay. So you just continue simulating the behavior of your machine M on the string W, okay, until it halts, and you know it'll halt because R told you whether it halts or not. Okay, so if M accepts, you have S accept, and if M rejected the string by simulation, then have S reject. Okay. Well. So that means that your S now is behaving as a decider of this language. Right? So if therefore, okay. So if R decides this language, then S decides that language. Okay. I hope that should be fairly clear. Okay, but we know that this is undecidable. So we have a contradiction, so we negate what we assumed, which was that halt is decidable. You negate that, therefore halt is undecidable. And if it's undecidable, there is no Turing machine R that can decide it. Okay. No, it doesn't say that. But therefore, halt. This language halt it must be undecidable. And there's the end of the proof. So I'll stop there.